1, 2, yep, there we go. So this was a slide I showed you last time. I added some pictures. And the exciting thing to you guys is everything on this slide you will see today. And it will be discussed. And the important thing was we're going to be talking about cheese sandwiches versus folding versus cutting cheese sandwiches. This is going to have such profound importance, you won't believe it. All right. And we're going to talk about cheese bits. So, like, you know, this is important stuff. And, of course, we'll talk about how to tell if a chicken is cooked. All right. Now if I can figure out how to use this. There we go. So we're going to do a quick review. As I told you at the beginning, I'm talking to you like your fellow knowledgeable geologists, not, you know, neophytes. So I'm jumping in at a really high level. So what I like to do is I like to review a lot, so you know, kind of absorb it a little bit better. This was one of our first slides last time, and we looked at this map and we noticed that there's lots of blue colors and yellow colors, and in general the blue colors are underlain by oceanic rocks, and the green are underlain by continental rocks, right? And then we said there's basically two types of, the blues are generally these basaltic rocks, and a basalt with fine crystals is called a basalt. It's a volcanic rock with fine crystals like this is called a basalt. If the crystals, exact same composition, but if the crystals are big, we call it a gabbro, meaning it crystallized slowly. So the blue stuff is underlain by the basalts or the gabbros, and then the yellow stuff, the continents, there's a whole bunch of different rocks in a continent, but in general, that's sort of the heart of the continents is loosely called granitic rocks. But here we're saying they're andesites, like the rocks from the Andes, the volcanoes from the Andes. Or if they're crystallized slowly, we call that a granodiorite, but you could just call them granite. So you can basically say that the blue colors up there are the basaltic or gabbroic rocks, and the yellows are underlain by more granitic rocks. The granites are lighter, and the basalts are heavier, so the basalts tend to float a little bit lower, and that's why the ocean basins are lower than the continents. The continents are also thicker. And we also reviewed the fact that basaltic lavas flow beautifully, and you can stand right next to them, but the composition of the andesites, the granodioritic or the granitic rocks, is such that when the volcanoes blow, you will want to be miles and miles away. They're very explosive. So if you're going to die in a volcanic eruption, it's almost certainly going to be this type, not this type, unless you trip over your shoelaces or something. And if we look at this same thing in cross-section, we have the thin oceanic crust, again made of the basaltic gabbroic suite, and then the thicker continental crust, which is, you know, loosely speaking, is more granitic in composition. And it floats higher because it's lighter and it's thicker. And then we'll talk about lithosphere and mantle and stuff later. All right, then we talked about the fact that the South America fits into the armpit of Africa, and we talked about the concept of continental drift and how it was really solved by this concept of plate tectonics and mid-ocean ridge spreading centers. So the fit between Africa and South America was explained by seafloor spreading in mid-ocean ridges. And the way we talked about this last time, the way that this comes about is basically there's a crack that forms, the magma comes in and fills in the crack, and then it's pulled apart. So these numbers 2 were originally together, and then they were separated by 1, and 3 used to be together and was separated by 2 and then 1. And what's happening is the mid-ocean ridges is cracking apart, new ocean crust is forming in between, and it keeps widening and widening until you have an ocean basin like that we see in the mid-Atlantic ridge. And the way they identified these age packages, what I numbered 1, 2, 3, 4, is all based on that magnetic striping that we talked about last time, because the Earth's magnetic poles switch periodically over time, and this is what it would look like as they measured it. So we're all happy with mid-ocean ridges? All right. And then we talked a little bit about we looked at a little video showing it, and let's watch an ad first, shall we? What's it going to be? No? Okay, so here we have here's the magnet. It's switching to south now. Okay, the seafloor spreading it, switches to north again, switches to south, and here's we're getting the magnetic striping. All right? And this is a fancier one. We looked at it last time. Okay, if we look at the distribution of mid-oceanic ridges, here's the famous Mid-Atlantic Ridge, but there's also an East Pacific Rise, and so on and so forth. They're all over the place in the planet, Southwest Indian Ridge and so forth. And we notice the fact that, hey, the Sea of Cortez has its one between Baja California and Mexico, and there's a little one off Juan de Fuca, off Washington, Oregon, and we're kind of puzzled by the fact that they just kind of end. We also talked about transform faults. So here we have this mid-ocean ridge spreading center, and you can see that the individual ridge segments are offset by this thing called the transform fault. And what's happening is this part of the ridge is spreading like that, this part of the ridge is spreading like that, and in this zone right here, they're actually moving against each other, which is a fault, and it can actually form earthquakes in that zone. Of course, the most famous transform fault is the... That's right, which is kind of different than this creature. We also talked about subduction. One of you sharp students pointed out last time is if we had only spreading centers, doesn't that mean the Earth is expanding? Well, we also have subduction zones that remove that expansion. So here we have our spreading centers, but we also have these subduction zones where the one plate is moving under the other plate, and eventually it'll get molten into the mantle zone. So as this Nazca plate subducts under, the barbs indicate the upper plate. So here we have this plate, and this is getting pushed underneath it, and eventually it will get melted and recirculated and recycled. All right. And there's basically two types of subduction zones. You can have a subduction zone under oceanic crust, or you can have a subduction zone under continental crust. In either case, as the downgoing plate partially melts, it feeds and forms these island arcs in the oceanic crust case, or andesitic margins like you'd see off South America in this case. But in either case, you're forming more or less granodioritic rock types above the subduction zone. So you have these explosive volcanoes that occur above the subduction zones, whether you're subducting underneath oceanic crust or underneath continental crust. And if we look here, this would be an example of this type of subduction, where you have subduction underneath a continent. And again, we have this line of volcanoes, which is the Andes Mountains. And then here we have the Caribbean island arc, the Lesser Antilles island arc, and this would be this type of island arc, and also the Central American. So this is an oceanic plate here, and it's got subduction on both sides of it. Earthquakes and... Was there a question? Nope. Earthquakes and subduction zones are very significant. So this is showing all earthquakes. You can see that you have earthquakes along ridges. Here's along the ridges. But you have lots of earthquakes associated with subduction zones, and they come in different depths. And the reason the earthquakes come in different depths is as the oceanic plate is subducted, it's going from shallow to intermediate to greater depths. So we see this chain of earthquakes that becomes progressively deeper as you go deeper in the subduction zone. And these deeper earthquakes are only associated with subduction zones, not any other type of boundary. Here's a cross-section through, this is Japan, Honshu, and this is Pacific Ocean, and here's this downgoing Pacific plate, and here's the earthquakes that you'd see, and they're going from very shallow depths to intermediate depths to great depths, and there's a final point at which you don't see any earthquakes anymore, and that's because the rocks are too plastic from being heated that they don't break anymore. To form an earthquake, you have to break the rocks suddenly. All right? But this is why you get these this parade of earthquakes associated with the subducting slab. This type of earthquake distribution is called a Benioff zone after this Caltech scientist who defined them decades ago, maybe 50 years, probably 70 years ago. But again, another local famous person. Here we've also labeled this. You can see here's why we talk about the lithosphere, because this is the oceanic crust and part of the mantle that's going down. So we're not usually just talking about the crust and the mantle anymore, because this subduction zone consists of the crust and the mantle. So that's why they had to define this term, the lithosphere, because they had to talk about how the plate tectonic motions were happening, not just on the basis of the simple original definitions of, crust, mantle, and core. All right, so again, the three types of plate boundaries, spreading centers, subduction zones, and transform boundaries, can be used to define these tectonic plates. The tectonic plates have to be completely bound by one of those types of features. All right, so every one of these plates, the Pacific plate, Nazca plate, South American plate, it has to be completely bounded by those types of boundaries. Now there's a North American plate and a South American plate. This fault is pretty, it's not really, basically North America and South America are acting pretty much in harmony, but they have to, apply that definition rigorously. There's also things called microplates, which are little tiny plates, which aren't shown on this. And we talked about one last time. What's the name of the one we talked about last time?
Santa Barbara.
Very good. Okay, so here's the three types of boundaries. We have the mid-ocean ridge type of boundary where you have spreading going on. You have the subduction zone where you have this type of motion, one plate going underneath the other motion, and this is the official hand signal for a subduction zone. And this is the transform, this is the official geologic symbol for a transform fault. So these are the three types of boundaries that explain, that define tectonic plates. We also talked about continental collisions and their role in formation of mountains. And we've talked specifically about the Himalayas, but we also mentioned Taiwan, Cuba, and some other places. So in the case of a continental collision, a continent gets stuck in a subduction zone. It's too buoyant to subduct, and it causes a great mountain building event called an orogeny. It's basically like clogging up your toilet and having a sewage spill because it won't flush. Or you can think of it in terms of an accident between cars, a collision. And you can now the interesting thing is this is a way to make a mountain belt by punching things together, but oddly enough, you can also make mountains by pulling things apart. And this is going to be very important today. So these are the mountains in Nevada, and these mountains specifically have not undergone squeezing, they've undergone being pulled apart. And it's this type of feature right here. So the arrows show the direction of being pulled apart, and what's happening is blocks are moving up and dropping down, and you still get this mountainous terrain, but it's not from classical squeezing. And they form very distinctive patterns. Okay, and then we said, okay, everything we talked about so far, from the different types of plate boundaries, the continental collisions and so forth, all of that's normal. And then we said California's weird. All right, and now we'll review that, why California's weird. So up in Oregon and Washington, we have a normal subduction zone like you'd see in Japan. There's a little spreading center offshore. This plate is bound by different types of features, tectonic features, so it's an official plate. Though remember, every tectonic plate has to have either a spreading center, a subduction zone, or a transform fault. So here's a transform, spreading center, subduction zone defining that plate. So this is normal. If we come down to Central America, we see a subduction zone here, another spreading center being subducted. But then we go to California, and all we see is the San Andreas Fault. And we go, wow, that's weird, because it's unlike anything sort of we looked at anywhere else on the planet. And here's a more detailed view. So everything looks sort of normal. Down here we have a subduction zone and a spreading center. Here we have a subduction zone and a spreading center. And here we have this weird San Andreas Fault going into a mid-ocean ridge separating Baja from Mexico, which is weird. And then we said, hey, look, you can push them right back together, and they fit just like South America and Africa. So then we introduced the hero of this whole class, who's Tanya Atwater at UC Santa Barbara, who I argued was perhaps the most famous woman geologist alive today, and one of the most famous geologists alive today. And she became famous by proposing this theory on the origin of the San Andreas Fault. Here's Los Angeles, where we live near. She proposed that that spreading center, that mid-ocean ridge spreading center, here's the subduction zone here, but prior to the San Andreas Fault, this spreading center got subducted beneath Los Angeles. Los Angeles is always in the news. And as that plate got subducted, the motions of the spreading center forced the creation of the San Andreas Fault. And this San Andreas Fault, as this Pacific plate was subducted beneath North America and Los Angeles, the length of the San Andreas grew and grew, and eventually we got opening in the Baja California area. Here's this big, long San Andreas Fault ending at what's called the Mendocino Triple Junction, which is off the coast of Mendocino. All right, so that was Tanya's theory, proposed in, I think, 1970. Sorry, that question? All right, and here's another picture of it. So here's this spreading center, just like the mid-ocean ridge, or like the mid-Atlantic ridge. It gets subducted under Los Angeles, always causing problems. And here's the San Andreas Fault that's the result of the motions. You can see the plate motions. As they get subducted, you form the San Andreas Fault, and then the San Andreas Fault grows and grows and grows to its present position until, in a change in plate motion, you get this spreading center that forms and separates Baja California from Mexico about 5 million years ago. And we said, okay, and then we said, one of Tanya's colleagues, Bruce Leyendijk, noted the paleomagnetism. He studied the magnetism in rocks in the Channel Islands off of Santa Barbara. And he said, normally if you study the paleomagnetism in rocks, they'll point towards the North Pole or towards the South Pole during the reversals. But instead, in the Channel Islands, they were pointing towards the East Pole, which didn't make any sense whatsoever. And they talked about it for a long, long time, and they finally came up with this interpretation that Santa Barbara had rotated. And it's this model right here that we'll review. Maybe after an ad, maybe not. 17 seconds. Oh, no, here it is. So this is Tanya's model. So what we do is we start off, and again, here at 20 million years, here's the subducted Pacific plate, and we're starting to form the subducted spreading center right here, and now we're starting to form the San Andreas Fault. Okay, now the Santa Barbara block, which is right next to San Diego, so Santa Barbara 16 million years ago was right next to San Diego. You could have driven there in 20 minutes. Okay, and with time, that block is going to rotate and continue to rotate. This block here is going to become San Francisco. It's moving north, like that. And here, here we're at 8 million years ago, up at the top. 4 million years ago, we start to rip off Baja California from Mexico, and then the Santa Barbara block slams into Santa Maria up here. All right? So that was the bizarre story of this micro block and how it tied into the evolution of Southern California. And that's the review we went into last time. But you all remember that, right? All right. Now, people have asked me, well, what's going to happen in the next, 15 million years? Is California going to fall into the Pacific? We've all heard that. Well, this young fella, he did his PhD in Arizona, and he's a professor down at Mira Costa, I think, college. And he wrote this, he did this calculation of what California might look like in 15 million years in the future if the San Andreas was the dominant pathway towards motion. And here we can see this is the Sea of Cortez expanding and now going up past Los Angeles in 15 million years. Again, we don't have to worry about buying property in Palm Springs yet. Here's another version. This is another fault system called Walker Lane, and here we'd have the ocean basin going up in a different direction. And this would be, remember those mountain ranges in Nevada? Well, in this interpretation, in 15 million years, the Sea of Cortez separation, or the little mini ocean basin there, goes up into Nevada, and it separates there. Now, you may look at this and chuckle, but these are all apparently, there's no reason why none of these can't happen 15 million years in the future, but of course, we probably won't know exactly. All right, so that was a quick review that took me 20 minutes, and now we're going to talk about how everything ties together. So now we're going to start talking about rocks in our neighborhood. All right? And we can look at the mountains in our neighborhood. So we all know where we are. We're here somewhere. This is Palos Verdes Peninsula, where I grew up. Catalina, here's the Channel Islands. Ventura, Oxnard, Santa Barbara. And also, that's San Andreas Fault. But if you go back, you can see the trace of it. So going into the Salton Sea here, and this linear feature coming up here. This is called the Big Bend, where the San Andreas takes a bend, like that. And then we can also add to this the names of the different mountains. This is the San Jacinto Mountains. We'll talk about these when we talk about the ice ages. San Bernardino Mountains, the San Gabriel Mountains. These are what are called the Transverse Ranges, or the Santa Monica Mountains. There's the Sierra Nevada Mountains here. And here's the Palos Verdes Hills, where I grew up, and I have an affinity for. And I'd like to bring up a point. The Palos Verdes Hills problem. Hill versus mountain, all right? According to the U.S. Geological Survey, there is no official difference between hills and mountains. The United Kingdom and the United States used to define hills as summits less than 1,000 feet. So a hill would be less than 1,000, a mountain is over. Palos Verdes, maximum height, 1457. Palos Verdes Hills are a low mountain range. So Palos Verdes Mountains, not Palos Verdes Hills, doggone it. So now I've changed this to Palos Verdes Mountain. All right. Remember that movie, The Hill That Was a Mountain? Okay, now we talked about this last time, the three major types of rocks, and we're going to look at this a little bit more detail today. Metamorphic rocks are any other rock that's been recrystallized through pressure and temperature. Igneous rocks are any rocks that were formed from molten fluid. So if you melt a rock and crystallize it, it's officially an igneous rock. Sedimentary rocks are basically ground down, weathered fragments of other materials that have been glued together, like sandstones, mudstones, that sort of thing, limestones. All right, so if we take a look at California, we see that there's basically three belts of rocks. There's these red rocks there's these yellow rocks, and then there's these blue rocks. These pink rocks here are basically part of the red rocks, but they've been moved up there by the San Andreas Fault, so we'll forget that. But in general, in California, there's these red rocks, the yellow rocks, and then the blue rocks. In cross-section, here's the red rocks, here's the yellow rocks, and here's the blue rocks. This is the general rock types in California really reflect what was happening before the San Andreas Fault. Before the San Andreas Fault, the continental margin looked like South America. We had a subduction zone, and we had a volcanic arc. And so the Sierra Nevada batholith is the uplifted arc of the continental margin, all right? So these are mostly granitic rocks, granodiorites, tonalites, diorites, that sort of thing. This yellow stuff was a basin. There was a big basin that filled with mud and sand called a four-arc basin, but we don't have to worry about that. And that's that yellow stuff here. And that's actually a valley today. So it was a basin 60 million years ago, 100 million years ago, but today it's still the same valley. So it's kind of, this great valley is sort of inherited from 100 million years ago, amazingly enough. And then this Franciscan subduction complex, we remember that during the subduction that we talked about last time, the stuff gets off-scraped, the goo gets scraped off like a snowplow or a razor scraping across your face or legs. And that's what the Franciscan complex is, right here. The Franciscan, so it's basically, these are the igneous rocks, these are the sedimentary rocks, and these are the metamorphic rocks. All right, so we have three belts. And this picture here is just a prettier cartoon than this. So this is actually from a paper that was written by a famous scientist showing what he thought the California margin looked like 60 million years ago, 80 million years ago. So we had a subduction zone, we had this Franciscan subduction complex that we'll talk about today, this great valley where Bakersfield is and so forth. And then we had this volcanic arc, which is today the Sierra Nevada. All right? And that's very similar to what we see today off of Oregon and Washington, where we have the Cascade Mountains, the Puget Sound, the Olympia Mountains, which are basically the metamorphics, and then here's the subduction zone. All right. So in the rocks in the Sierra complex, if you go into the red stuff, this would be Yosemite. These are these beautiful granitic rocks formed from melting associated with the subduction zone. Now, when I say that there's three belts of rocks in California, I'm speaking very broadly, and if you look at details, you'll see there's all sorts of different complex rocks and types that we geologists love to worry about, but we're looking right now for just the big picture. And by the way, I don't know if you realize this, there's these things called geologic maps. We were just looking at one a minute ago from the Pyrenees. And what they are is they're geologic maps, and they basically make a map and they color in what types of rocks are found in any particular area. So again, if you're in Yosemite, what you'd be seeing is lots of granitic types of rocks, because that's what Yosemite has. But if you're going to Palos Verdes, you might see this a map showing these brown rocks that we'll talk about today, and so forth. The maps also have different scales, so if you're looking at a little tiny detailed area, you'll see lots of fine detail, but if you're looking at the whole state of California, they generalize it and make it more simple. But this is an example online of all the different geologic maps that are available of our area right now. All right, so we're going to start talking about rocks. We gaze around us. What type of rocks do we see? Let's first talk about Catalina Island. This picture here is from a surf cam where they're looking at the waves here, but I thought, you can see the island of Catalina offshore. Here's a satellite image of Catalina and an up-close picture of Catalina. So Catalina, here's a geologic map of it. Basically consists of two types of rocks. These colorful rocks are metamorphic rocks, and these brown rocks are younger volcanic rocks formed from a melt. So these are older metamorphic rocks that were cut later, intruded by this volcanic succession. Now, these rocks on Catalina are very peculiar. Here's a picture of them. There are a few types of rocks found in Catalina, and the most famous is called the Catalina schist. The Catalina schist is a metamorphic rock of Cretaceous age around 60 million years ago. That was formed it was formed at a depth of about 15 to 45 kilometers, around 20 to 30 miles. So the rocks in Catalina were formed at a depth of around 20 to 30 miles beneath the crust, and somehow brought back up to the surface of the Earth. The Catalina schist is known as a blue schist because it's kind of got a bluish color to it. Blue schists are very important in geologic studies as they tell you something. They also, you can also see these same rocks on Palos Verdes Mountain. All right, so here's some pictures of blue schist, so you can see why they call it a blue schist. These are microscopic images of, this is the mineral glaucophane showing this bluish color, and these are hand specimens and outcrop. All right, so they've done mapping of this Catalina schist, and they think it forms a whole belt. Here's the island of Catalina. Here's Palos Verdes up there. So they think this whole area, if you drilled a well down there, you'd find Catalina schist eventually. Right? We're going to get to why this is important. Here's another map showing where they think it occurs. Places you can see Catalina schist. So what they've done here is they made a little black dot wherever they've seen evidence of the Catalina schist from drill holes and so forth. So there's a big belt of rocks with Catalina schist. All right, so let's see. Let's just skip to the next slide. So this was that figure we looked at, talking about the Franciscan assemblage, the Great Valley sequence in the Sierra Nevada. The rocks, the Catalina schist on Catalina is part of the Franciscan assemblage. So here we have Catalina and these blue schists. At the same age and the same time, we have granitic rocks in the San Gabriel Mountains. So here we have molten rock that's slowly crystallizing to form granitic rocks. And here, 40 kilometers away or 30 miles away, we see this squeezed rock that's present in a subduction zone. All right? And they think it's due to this subduction zone that's occurring. So we have the Pacific plate is being subducted, goop is being scraped off and buried and getting squeezed, and that's why we see that Catalina schist. All right, so what they've done is they've studied the minerals in the Catalina schist, and doing chemical studies, they plotted the temperature that the minerals are stable at versus the depth or the pressure. And they found that all the minerals on the island of Catalina, in the blues and the reds and the greens up there, were formed at depths of 10 to 20 to 30 miles. So it's deep in that subduction complex. So 30 miles down is, well, from here to, if you're on the coast, from Huntington Beach to Catalina is 26 miles across the sea. Well, now if you took that and you went vertical, that's how deep Catalina was when it formed. Right? So this is why, so the idea is the rocks on Catalina are stable only at depths of around 30 kilometers. So therefore, the only place that they think that they can form is in one of these subduction zones where you have cold rock being pushed to great depths. So the characteristics of a blue schist is they formed at great pressures but at relatively low temperatures. So they didn't melt. Otherwise, they'd end up like the San Gabriel Mountains and just be molten rock. So that's why these blue schists on Catalina are so unique, because they're high pressure, they formed at great depths, but in a relatively cold environment. No melting. So we can in fact generalize all blue schist metamorphism in the world over all time was formed in a subduction zone. So whenever you give me a piece of blue schist, I can say, this was formed in a subduction zone. It's the only place they form. Kind of cool. So we explained that problem. We went to Catalina. We looked at the metamorphic rocks. We plotted it on this pressure depth diagram, said they were formed in a subduction zone. The belt of Catalina schist represents part of an ancient subduction zone. We're done. We can go home. We've solved the problem.
We know you too well.
But the next new geologic problem, okay, we've identified the rocks on Catalina as forming at great depths under lowish temperatures like 20, 30. Did I lose something? There we go. Am I back? Yep. All right. So we got the Catalina schist forming at great depths and at cold temperatures 30 miles down. How do we get it back up to the surface? How do you get rocks that are 30 miles down or 20 miles or whatever it is and get it back up to the surface? Well, those scraping got it down, remember? So we had the subduction zone, and that pushed it down, and that took stuff that was at the surface and pushed it down 30 kilometers. How do you get it back up? But it's not very buoyant. If you stuck a volcano in there, it would change, they wouldn't be blue schist anymore. Rifting. Rifting's hot, usually causes heat. Let's talk about cheese. A classic problem in geology questions how rocks that we know were formed at great depths in the earth, some as deep as hundreds of kilometers, are exposed at the surface of the earth. While we are at it, let's talk about cheese and toast. If the toast is the surface of the earth and the cheese is what is beneath the surface in the mantle of the earth, how do we ever see cheese on the surface of the earth? So toast, cheese, how do you get the cheese up in to the top of the toast? The cheese is between the toast layers. How do we ever see the cheese? The same concept can be applied to rocks. How do we ever see rocks that are once deeply buried? All right. So the original theory of how you got rocks from great depths up to the surface was by squeezing them and folding them. So you take the crust, here's the cheese, and you squeeze them together. Here's the crust and there's the cheese, right? But it doesn't really work because all you've done is you've mushed it together and there's still a bunch of crust on top of it, right? So does squeezing by collisions unroot deeply buried rocks? If you imagine you're trying to get the tire up on top of the hood of the car, smashing together the car doesn't get the tire up. It crumples it, but it doesn't really get the tire up higher. So deeply buried rocks are often found in mountain ranges formed by continental collisions. However, you have to erode off the entire mountain range to get down. And the amount of sediment that you'd form, the sand and the mud, is enormous. Miles and miles of the stuff. So most people don't like the idea that collisions unroof rocks, bring rocks up to the surface. Enter John Platt from UCLA. This guy's a professor right now, just like Tanya is still at UC Santa Barbara and Lyondike's still at UC Santa Barbara. This guy's at UCLA. And he argued that smashing things together does not bring things up to the surface. So the folded sandwich doesn't work. What he proposed is that pulling things apart brings things up to the surface. So what he said, it's not collisions that bring rocks up from the deep. He says it's by pulling things apart. And this is a radical idea. Like no one had ever thought about this before. It seems obvious now, like, well, look, there's cheese, you know. But when we read this paper, actually, I was working with a grad student at the time, and we came up with the same theory. We said, oh, we figured it out. And we went back and Platt had published, and we were like, oh, he beat us. Well, he is half a year in front of us. So faulted sand, even having faults and earthquakes and so forth, doesn't bring the cheese up to the surface. But this was a picture we talked about last time. This is an example that we said that happened out in Nevada. As you pulled the rocks apart, you can see this blue area gets closer to the surface. It's originally buried 15 kilometers. Now it's only buried maybe 8 kilometers. Now it's only buried maybe a couple of kilometers. So by pulling things apart, you get the cheese to the surface, right? So what's being pulled apart? Well, Santa Barbara is rotating away from San Diego, and this whole area is getting pulled apart. So during the rotation of the Santa Barbara block, the area behind the block was stretched and stretched, eventually exposing the Catalina schist, the Franciscan Formation. Additional stretching occurred because there's another event going on at the same time. All right, this was the Tanya video that we looked at last time and this morning. So there's the extension. I searched the internet trying to find a picture of a cheese sandwich being separated like that, and I finally found that one, which kind of shows the Santa Barbara block pulling away from San Diego, and that gap in between is where the LA schist, the Catalina schist, and the LA basin is. I mean, I'm a dedicated cheese aficionado. Okay. This guy is John Suppy. He's a world-famous geologist from Princeton. Again, still there. This is all active stuff. And he, with I guess one of his graduate students, I couldn't find a picture of Crouch, back in 1993 proposed this add-on to the Tanya Atwater model. What was known, here we are, here's Palos Verdes, here we are, San Joaquin Hills are the hills right over there. Here's Catalina, here's the Channel Islands. Remember, with the 90-degree paleocurrents towards the East Pole. And one of the things they'd noticed was on the island of Santa Rosa, there's a rock formation there that looked identical to a rock formation in San Diego. They said you could just take one hand and one and the other, and you could not tell them apart. And everybody was like, wow, that's weird. I heard about this. This is called the Poway conglomerate, and this is the Poway conglomerate on Santa Rosa Island. I was told about it way before. I heard about this back in the early 80s, and we were all like, wow, that's weird. And that's all we could figure. We didn't know what to do with it. So anyway, what Suppy proposed was this. Here's the Poway conglomerate. This is what it looks like. It's a rock composed of pebbles. Conglomerate, so they're rounded pebbles, probably from stream erosion. It's about, 40 million years ago. And what Suppy and Crouch argued was that this is the Santa Barbara block, and they're saying that these rocks here match up with these rocks here, so all you have to do is bring them back. Here's that 90-degree paleomagnetic declination, the change in orientation, and that sort of solves the question. And it's kind of hinged right here, so this is just kind of opening a little bit, and it's really swinging out a lot more in that direction. All right? So that was Crouch and Suppy's proposal, and again, that's tying to this sort of feature right here. It's the exact same picture, essentially, only they're putting in geology now. All right, now, Suppy and Crouch, or Crouch and Suppy, also made some cross sections like that. And what they're arguing is, here's our cheese sandwich model, and here's their cross section, shown in red up there. And they're saying if you sliced apart this area while the cheese sandwich was being pulled apart, you'd see this gigantic fault, which is where things are getting pulled apart. And then here's these different features. You've ripped it. Remember, you're ripping a hole 30 miles deep because you got to pull the Catalina schist up. This is the Catalina schist coming to the surface. So this has enormous significance, and you're actually cracking in, and you're getting volcanics coming up. These are volcanoes that were formed. This is way up in Santa Monica Basin. And here we are off of, this is basically off. Here's Cristiano's Fault. This is the San Joaquin Hills, which is essentially the hills of Newport, Irvine, right behind us here. And so here's this gigantic fault, the pulling apart fault. Here's some volcanic materials. This is in Palos Verdes Mountain, all right? And here is this Wilmington Graben, which is going to become essentially the Los Angeles Basin, and so on and so forth. and it's the cheese sandwich model. So again, this is that same model being applied to the evolution of the Santa Barbara block. And now these two guys, Eric Geist and Rob Bohannon, shown there, they went and looked at ultrasound data. This is called seismic reflection data, and it's basically like the ultrasound you do of your organs, your babies and your hernias and all that sort of stuff. This is essentially an ultrasound feature, but we call it in geology a seismic reflection profile. And they saw this type of feature, and they said, aha, I can identify that master fault that Suppy proposed. So Suppy and Crouch proposed this enormous fault without really seeing much evidence of it. And then Bohannon and Geist went and they said, well, we can actually see the fault, and this is the fault that led to the Catalina schist rising up to the surface, 30 miles, 20 miles. And here's another example. So the top is the actual data, and here's their interpretation. This is called a detachment fault, where you're pulling things apart, and you're bringing up the Catalina schist basement. All right? Here's another example. So, results of ripping the earth apart accompanying rotation of the transverse ranges. Island of Catalina, rocks exposed there were formed at 15 to 45 kilometers depth, 20 to 30 miles. Geologists long wondered how you could bring rocks that were buried so deeply back to the surface. If you simply uplifted them, you'd have to erode off miles, 30 miles of rock. And where is that sand that you'd erode? And by ripping the earth apart, you can bring the deep rocks up to the surface without uplifting them, so by pulling them apart. And that's just Tanya's same model. So the rocks in Catalina came to the surface accompanying ripping the earth apart, extensional tectonism, during rotation of the Santa Barbara block. All right, so here's the rocks in Catalina, the blue schists, and the argument is they're being brought to the surface by the earth being pulled apart during the rotation of the Santa Barbara block. We all good on that? The next question you could ask is, well, when did all this ripping occur? We know that based on radiometric dating, isotopic dating, we know that the Catalina schist is about 100 million years old. But how do you know when it got back up to the surface? How can we tie it into Tanya Atwater's model? How do we know when the blue schist rocks actually came up to the surface? Here in the Crouch and Suppy model, these rocks are bits of the Franciscan complex. So basically, what we're asking is, where are the cheese bits? So if you have a cheese sandwich, we won't see the cheese until you break the sandwich apart and you expose the cheese, and then you can get little cheese bits dropping down. See what I'm pointing? If the cheese is captured between the pieces of bread, you don't see the cheese. But when you pull the bread apart and you see the cheese, then you can get pieces of cheese. Am I being too allegorical here? So, at any rate, the idea is that Crouch and Suppy said is there's this weird rock unit that occurs along the coast here that we're going to look at. It's this rock right here. This rock here, this is called the San Onofre breccia, and it's not completely, but it's largely composed of chunks of the Catalina schist. So we can date this rock and we can say, well, obviously the Catalina schist had to be at the surface because now the pebbles and so forth that are coming down are from the Catalina schist. All right? So Crouch and Suppy argued that you could date the timing of the detachment, the pulling apart, by when this San Onofre breccia formed. Okay, as the Franciscan rocks were uplifted to the surface during the ripping, they formed huge boulder beds and pebble beds called the San Onofre breccia. The San Onofre breccia, by the way, named after San Onofre, can be seen in the northern coast of Laguna Beach. I could take you there in 20 minutes, and Dana Point Harbor. All right, it's one of the most bizarre conglomerates I've ever seen in my long life. This is Dana Point, and these entire cliffs are these pebbles and blocks of eroded Franciscan or Catalina schist, indicating that the Catalina schist was now at the surface of the earth and was being eroded by streams and gullies and that sort of stuff, forming these deposits here. And as I've said before, this place is so magical that you definitely want to get married there. All right, so again, all these rocks here are these chunks of rocks derived from the erosion of the Catalina schist, and these happily newly married people thinking about their life in the San Onofre breccia. There's a study that was done by this guy Charles Stewart, I think in 1979, and he mapped out all the different places where you could see the Catalina schist and what the age of the Catalina schist was. And again, the Catalina schist is the cheese bits. Okay, so the Catalina schist, Franciscan Formation, was uplifted during extension behind the rotating Santa Barbara block. So here's the rotating Santa Barbara block bringing up the Catalina schist. And the erosion of the Catalina schist formed the San Onofre breccia, right? What next? At 12 million years ago, a giant basin forms where the ripping occurs. Okay? So you're ripping a hole that brings up these deeply situated rocks, and that's formed this giant basin, which is our own Los Angeles basin. You can still see it here today. I have no idea what this video is. Let's see what it is. Probably a commercial for Nike or something. No, it's the same. Okay, this is just showing the block ripping apart again. So this is the extension that's going on, that's ripping and bringing up the Catalina schist, which will eventually lead to the formation of the San Onofre breccia. Now we have a basin to fill. I'll go on a little bit more. Results of ripping the earth apart, accompanying rotation of the transverse ranges, part 2. How about if we take a break? Is that a good idea? Where's Gary?
Right here, 10 minutes. You can decide.
We ready? All right, so as we mentioned last time, Santa Barbara block rips away from San Diego and leaves this big hole, and that's what we call a basin. So I have some videos on what a basin is. I haven't got any commercials yet. This is amazing. Okay, so what they did is they took this box here. Are they going to do something? Oh, God. Okay, and what they did is what they've done is they've put in sand layers here, and they've got a crank, and they're going to pull the rocks apart, and they've already got some pre-existing geology to make it more realistic, strong crust and so on and so forth. So anyway, as they pull it apart, you can see you're forming a hole there, which is and then they're putting in different colored sand to make different types of layers. And what they're doing is they're forming a low spot here, and this is called a basin. So the idea is that as Santa Barbara pulls away from San Diego, it's leaving a hole behind, very similar to the hole formed from this sandbox model being extended, right? And as you're pulling the box apart, sediments raining in and filling in the hole, right? And that's what they're showing here. So this is how what's called a geologic basin, you can see it continue to form here, and here's his hand going around and around, and the different layers forming this basin, and that basin is basically our Los Angeles basin that's forming by the rotation of the Santa Barbara block. And now he's got faults in there and all sorts of stuff. Geologists have lots of fun playing with sandboxes and so forth. And I wonder what this one is.
The Basin and Range Province is a...
All right, we're not going to talk about it. So, back to the Crouch and Suppy paper. So here is y to y prime is this figure right here. And you can see that red oval there. That is this area here, the Wilmington Graben. So the idea is as you're moving the Santa Barbara block away from Santa Barbara block away from San Diego, you're ripping this hole. Here's the future Palos Verdes hills. Here's the San Joaquin Hills. And this basin that's forming in between is essentially the Wilmington Basin, which is part of the greater Los Angeles Basin. So the formation of the Los Angeles Basin, the Wilmington Graben, is all associated with this rotational behavior.
Excuse me.
Yep.
What is Anaheim noise? Nose. Oh, nose.
Anaheim. Oh, that's the question is, what is Anaheim nose? And I suspect, I can't remember, but that's probably a squeezing feature, like what we call an anticline, a fold. All right, good question. Okay, so again, we're forming this basin. Here's the future Palos Verdes hills. We've got the Catalina schist being uplifted during the extensional deformation. We've got volcanic material because we're cracking a hole. I mean, remember, you're bringing up stuff from 20, 30 miles down. You're cracking the Earth's crust, and you've got hot magma coming up and forming volcanic rocks in the Palos Verdes hills. And then there's the San Onofre breccia, the detritus of the Catalina schist, and these other rocks on top of it. This is called the Monterey Formation on top of it, and they're deep water mudstones. Oh, now don't go jumping ahead. This is Abalone Cove. This is the Wayfarers Chapel. Glass Chapel is right about here. And this picture is very meaningful to me because I grew up at Abalone Cove. I was a beach boy, a janitor, and I cleaned the garbage here at the beach for about 6 years through junior high school and high school. So, but at any rate, what you see on the cliffs here, this is a big volcanic succession here, a sill, an injection of molten magma that froze. And then these layers of rocks here and also down here is this Monterey Formation, which are the deep water muds. So this is an example from the last picture. The last picture. We said that the Catalina schist is being uplifted. There's detritus coming off, and we're looking at the relationship between these volcanic rocks and these deep water mudstones on Palos Verdes. And that's what we're seeing in this picture, deep water mudstones and volcanic rocks. And this is at Point Furman, which is a few miles from Abalone Cove. There's the Point Furman Lighthouse. There's old Catalina offshore. And these are all volcanic rocks and the Monterey Formation as well. So as you ripped Santa Barbara and San Diego apart, bringing up the Catalina schist, you cracked the Earth's crust, and you've got molten magma coming up, and you've got these deep water mudstones mixing with volcanic materials. Now, what about, yes?
Why didn't the LA Basin have schist coming up as well? It just wasn't deep enough to let it up?
Good question. Essentially the LA, it's a little bit off center, but the LA Basin would be sort of here. Essentially, you're just not at the position. You're basically the extensions the uplift is happening here, and the LA Basin's a little bit off to the side. So the reason is the LA Basin doesn't have the same sort of features as you'd see in Palos Verdes. It's just away from the center of that type of motion. Not a very clear explanation, but essentially LA Basin's here, and this is Palos Verdes over here. Or here's the LA Basin here. You're just way above all the activity. So LA Basin's going to fill with miles and miles of sediment, so we never would see the Catalina schist. That's the correct answer. So this would be the LA Basin, and there is Catalina schist, but it's miles and miles beneath it. And the only reason we see it in Palos Verdes is it's been uplifted. That's the right answer. Sorry, it took me a while to get my thoughts together. Okay, here is the magic rocks that filled the Los Angeles basin and the chalk cliffs of Newport Beach. So this is the back bay. There's a road here that you can drive, and these white cliffs that you can see are chalk. So forget you, Dover. We got our own Newport Beach chalk. Okay, these are chalk cliffs. Unlike the chalk cliffs in England, which are made of calcium carbonate, like seashells, the chalk cliffs of Newport Beach are made of silica glass and are called diatomite. All right? Diatomite is from diatoms, which are basically a type of marine plankton. All right. Now, diatomite, if you say it wrong, sounds like dynamite. But diatomite. All right. All right, so here's the Monterey Formation, Newport Lagoon, California. So again, this diatomite is in the Monterey Formation. It's a chalk, and we can see it in the back bay. Now, you might ask yourself the question, how come Palos Verdes has those cool volcanic rocks that I showed you at Point Fermin and Abalone Cove, and we don't have any in Newport Beach, Laguna Beach? Did we get gypped? And the answer is no. This is Crystal Cove going into Emerald Bay over here. You've all seen this. This is the Monterey Formation right there. This is an intrusive body into the Monterey, and this is an igneous body, just like we see in Palos Verdes. So in the San Joaquin Hills, we also see this intrusive volcanic material cutting into the Monterey Formation. Yep.
Every time I drive by that cliff, that's volcanic. Every time I drive by that cliff that's volcanic, I keep thinking that doesn't look like it's going to erode away in the next century. What do you think?
That's a really good point. This stuff is much hardier than this stuff. The Monterey Formation is a very soft rock. It can slide. A lot of the famous landslides in California, in Southern California, are associated with the Monterey Formation. But the Monterey Formation will pay us back. I'll explain in a minute. This stuff, looks nasty, hard, and very unerodable. Good point. Okay, yep. Oh, that's a geologist. It's going to be a hard question.
That's where most of the oil comes from.
I teased. God, you just spoiled it. Okay, and let's not forget Catalina. On the island of Catalina, all that brown stuff is more intrusive igneous rock. All right, so as we crack apart and form, Santa Barbara from San Diego, lots of volcanic material. One of the weird things is during Monterey time, when those muds were deposited at Abalone Cove and down at Laguna Beach with Crystal Cove, if you go up to Northern California and look at the rocks, there's never any volcanism. Whereas around here, there's tons of volcanism, and I grew up with this. In fact, as I told you, I grew up in Abalone Cove. In my backyard, there was literally a volcanic rock and I had the Monterey Formation with fossils in it and volcanic rocks in my backyard that I still own today. And one of the questions is everywhere else in California you see the Monterey Formation, you don't see volcanic rocks. It's just in Southern California, and it's because that's where the rotation of the Santa Barbara block occurred. Okay. All right, so the Monterey Formation. The Monterey Formation is widespread across California. It goes actually into Alaska and Japan. It was formed during a period of enhanced coastal upwelling. The Monterey Formation is magical in that this type of rock is what's called an oil source rock. A large fraction of all the oil in California was created from the Monterey Formation. All right? And here we said the Monterey Formation. The Los Angeles Basin is the most productive basin by area in the world, including Saudi Arabia. And the Miocene Monterey Formation, which is exposed along the coast and in the hills of the Palos Verdes Peninsula, is the most prolific source rock for this basin. Okay, so you guys, like most of us here, have forgotten your history of LA Basin. Okay, so let's talk about how the Monterey Formation was deposited. This is what diatoms are. Again, they're formed from this weird algae. They form these little crystalline skeletons, only they're plants. They're not really animals. And they're very beautiful. Did you study diatoms as well? Yes. Okay. And this is what diatomite looks like, as Gilbert mentioned earlier. You can make kitty litter out of it. It's very important in the kitty litter industry because it's very porous. If you put your tongue to this, it just sticks to it because the porosity is so.
Is that what they use for swimming pool filters?
I think they do as well, yeah. So they use this for swimming pool filters as well. Anyway, the way the Monterey Formation was deposited is very interesting. What happens is we had some sort of coastal system that was blowing. As the Earth turns, what happens is the wind's blowing this way and the Earth's turning that way, Coriolis forces. We get deep water upwelling. The deep water is nutrient rich. We have tons of sea life as a result. There's so much activity from the sea life associated with this deep water upwelling that you have it all falling down to the bottom, and it forms these organic rich mudstones which form oil. Okay, that's
Back in which time period again, please?
the Miocene 10 million years ago. Okay, so again, we have these wind currents, and we have Coriolis forces associated with the rotation of the Earth, causes deep water that's nutrient rich to upwell, that causes great plankton blooms, fish swarms. That's why their fishing was so great in the Southern California. And as all these life forms die and go to the bottom, it can form anoxic zones that preserve the organic carbon, and that those anoxic muds are key in the formation of oil deposits. All right, now this is the Newport Back Bay. So here's the Coast Highway, here's the Back Bay, here's those chalk cliffs we were talking about. Jim Ingle was a buddy of mine. He was our chairman when I was at Stanford, and he was one of the paleontologists who studied the Back Bay of Newport, at the Newport Back Bay. And he looked at the ages of the rocks and the formation of these chalk cliffs. Okay, this is the Monterey Formation at Crystal Cove. This is what the Monterey Formation looks like. Here it's thin-bedded mudstones mostly. Here it's been contorted by tectonic forces into tight folds. Here's some more folds like that, but this is all Monterey Formation. All right, so let's take a look at this a little bit. This is how upwelling occurs. Holy mackerel. All right. So what they're going to do is they're going to put in an ink, and apparently they're doing it in several steps, and then they're going to blow a fan across the water. And what they're showing is here's the wind blowing on the water, and then you have preferential upwelling associated with the wind blowing the currents away from. So the idea would be the shoreline is here. Here's the ocean level. The wind's blowing this way, and you're upwelling here, and that forms these nutrient-enriched zones. And that's the basis of the idea of coastal upwelling. Let's see what this figure is. Oregon State. I suspect there's words. So here is again the wind direction here, and there's the Coriolis forces taking things offshore, and here's the nutrient-rich waters coming up, and you get lots of enrichment in marine life here that forms that the upwelling currents bring nutrients to the surface, and the growth of microscopic plants called phytoplankton. They bloom and fuel and produce a food web. The phytoplankton eventually sink towards the seafloor where they decompose, giving up oxygen, forming these anoxic layers in the subsurface. All right, good enough. So that's the concept of upwelling and how it leads to mudstones that have lots of oil in them. If you go down to, this is Pirates Cove at Big Corona Beach. And this is a famous rock formation that's used in numerous movies, including one about a mermaid, as I recall. This is a sandstone in the Monterey Formation. So we said that the Monterey Formation, like at Abalone Cove, was formed in deep water. It's a deep water mudstone. How do you get a sandstone in deep water? So here's a question for you. If you had to figure out where there was sandstone in the middle of the ocean, if sands come from land and you're in the ocean, how far out in the ocean can you go and still see sand? So if you're a mile offshore, is there any sand? Now quit that, Gil. You're doing it again. Okay, if you're a mile offshore, if you're 10 miles offshore, is there going to be any sand? If you're 100 miles from shore, is there going to be sand? How about 1,000 miles from shore? Will you see sand? Does that sound impossible that sand, if you drilled down and found a big thick pile of sand 1,000 miles from the nearest continent, would you be pretty amazed? Come on, you'd be amazed. Right? Because you're kind of thinking, well, sand is where beaches are, and if you go offshore, there's not going to be any sand because it's all on the beach, right? How do you get sand in the middle of the ocean? Okay, so at Big Corona Beach, this is at Pirates Cove here, there's a sandstone body, and the sandstone body is mixed with deep marine mudstone. How did the sand get into a deep marine environment? Well, that's a good idea. You've got your father's roots. Okay, so here's Big Corona, and this is, again, a deep water sandstone. All right, the Monterey Formation was deposited in deep water. How did the sandstones get there? Another famous geologic problem, just like how deep crustal rocks get up to the surface. Another famous geologic problem is the occurrence of sand in deep water settings. How far away from land can sand be found? And most of you laughed when I said 1,000 miles. We know sand occurs on beaches and deltas and rivers, but how would sand get into the deep water? Can it get a mile out to sea? 5 miles, 500 miles, 5,000 miles, he said emphatically. So there's a thing called a submarine fan, and the idea is that you can get these bodies of sand that are well offshore. All right, and here's an example from remember the seismic profiles like we saw for offshore of California? This is one I stole from the oil industry, and you can actually image these rivers of sand coming down off of Africa here. These are actual blocks in the rivers up to the size of cars and buses, and they're moving into deep water. This image is essentially an ultrasound image like you'd see in a pregnant lady, only much larger scale. This is what's called a 3D seismic image. And it's showing channels going out into deep water. So these are called submarine fans. You can see very great details like a meandering geometry of the sand bodies. So they're basically submarine rivers. And what they are, as Gil led on, as turbidity currents. I'm just teasing you, Gil. And here's what a turbidity current looks like. It's basically a density current, so it's one heavier fluid flowing underneath another fluid. So here's the turbidity current coming down. It's turbulent. That's why they call them turbidity currents. And you can see that it's moving into deeper and deeper water. Here it's smacking up against the end. All right? So this is how we think sand gets out into... Now here's the head going in different direction. So this is basically two different density fluids. One is flowing under the other. Here it's coming right at you. All right? Okay. Let's see. Anything else here? So that's the concept of turbidity currents. Oh, here's another one where they'll come down. Here they put topography on the bottom of the basin. So when the flow comes down, it's going to be over a bumpy surface. So here it's coming down. All right. So it fills in the little low areas a little bit more than on the high areas, of course. And here you can see the little fill that happened there. I love turbidity currents myself. Okay, here's another example where they've got green going into the blue areas. So the same idea is these are density currents where one fluid is more dense than the other, so it goes underneath it. And it can transport sediment down. Yep.
Is the sand contemporaneous with the Monterey Formation?
Yes, it's within it. It's
Same age.
same age. Yep. All right. Turbidity currents can deliver sand 1,000 miles offshore or more. So this is the most famous one in the world. This is the continent of India. This is called the Indus fan. This fan body, which is, as long as India, 1,000 miles or more in length, has channels in it that are these submarine channels that are fed by density currents. And we've got sand coming down for, 1,000 miles or something like that. So this is how sand can communicate from land masses into the deep ocean basins. So that's called the Indus fan, and that's called the Bengal fan. And there are these channels that are 1,000 miles long, and they're fed by these density currents flowing for 1,000 miles underwater, carrying sand. Amazing stuff. So that's how we think when we see these sandstones of Big Corona. This is the process we think we have sand bodies within this deep water Monterey Formation. Here's Little Corona. You have to, if you show Big Corona, you also have to show Little Corona. Everybody loves Little Corona because of the arch offshore. And this is all the same Monterey Formation. Okay, so the rotation of the Santa Barbara block formed a big hole in the crust, the Los Angeles Basin, and we said it all filled in that. When you have a hole, you fill it in with the different sediments. This basin filled with the Monterey Formation, which was a source rock that we said, remember the diatomite, formed anoxic zones where you had these organic carbon-rich muds. And we also had sands coming in, these turbidity current sands. So we had this basin forming here that's got organic-rich mudstones in it, and it's got sandstones in it from the deepwater turbidity currents. And we see the Monterey Formation in the Back Bay and at Crystal Cove and at Corona del Mar Beach. Okay, now, sometime after deposition of the Monterey Formation, which attains thicknesses of thousands of feet, especially in the LA Basin because it's a big hole that needs to be filled, Southern California got squeezed and deformed. So these folded rocks here are from this period of shortening that occurred after the rotation of the Santa Barbara block. Unfortunately, we don't really have an event that we can say, oh, that thing caused the shortening. Back in 1980s, we had an idea of the cause of the deformation, but it was disproved. So we don't really know why the Monterey Formation got squeezed and the San Joaquin Hills are deformed and so on and so forth, but they are. And that has profound significance.
Can I have a-
Yep.
In areas where there are huge faults, sometimes you can find compressional, as you approach the fault, you'll find compression at the edges of the fault, you find huge compressions.
Yes, but this is a regional event, and and there are faults going on. But remember, during a lot of the formation of the San Andreas Fault with the rotation, you have extension going on, which should not form that type of feature. So something changed where we went from mostly extensional deformation to more shortening deformation. Strike-slip faulting should not form this type of deformation, ever. This is real shortening. And I don't really know what causes it. So anyway, before the rotation of the Santa Barbara block, remember we had something where we had the subduction zone, here's the Catalina forming, Here's the San Gabriel Mountains, more granitic rocks. And then after deformation, this is what it looks like today. So this is a study done showing, here's the Los Angeles Basin. Remember, as we pulled apart Santa Barbara, San Diego, we formed this big hole. Well, we've got miles of sediment filling the LA Basin now. But during this shortening event that caused those folds at Crystal Cove, you can see all these blocks got smushed together. All this purple stuff's the Catalina schist. All this pink stuff and brown stuff is the stuff underneath the San Gabriel Mountains. So that beautiful picture that we started off with, here. So we take this model here and we squeeze it during that event that I don't understand. And that's what we get here. And that's what we see today. So this is what we see today as you go from the Palos Verdes Hills here. See, it says Palos Verdes Hills Mountain. And here's the San Gabriel Mountains over here. All right, so, and this is simplified too. So, but it got squished and crushed, and we really don't have a good idea why, that I know of. Yep.
How does the Newport Inglewood Fault fit in?
Oh, we're going to talk to death about the Newport Inglewood Fault, but next time. All right? We're going to talk, that's all we're going to talk about next time. But the Newport Inglewood Fault, actually it's on, I'd have to go back and find it. It's problematic at this point. And it's actually problematic. Excuse me? Yeah, okay, but tying the Newport Inglewood Fault into this history is problematic, and we'll talk about it, okay? That's all I can do is promise you. Okay, let's talk. This is the famous chicken thing. So we're going to take a little break now. It's 3:30.
No, we just did.
What's that?
We've had our break, we only get one.
No. I mean, we're going to take a mental break now. We're not going to take, this is not a 2-break class. No, we've been talking about rocks, and I thought sometimes, you talk about rocks for a while, and then you want to talk about food, right? You get a little hungry, you think, schist, gabbro, let's talk chicken. All right. And the thought question I have during our mental break, not physical break, is if you take a chicken and stick it in the oven at 300 degrees Fahrenheit for a few hours, what happens? All right. So how do you tell if a chicken is cooked? A short presentation for those of you that may not know. Telling when a chicken is cooked by color. So we start off pink, it goes kind of yellow, orange, orange-brown, brown, and then it gets black, right? All right. Let's number the chicken colors. All right, I numbered them 1, 2, 3, so on and so forth, right? Raw to burnt. We're all in agreement? Yep. All right. Please note the potatoes would cook in a similar fashion, or turnips or acorn squash. This is a quasi-universal law of cooking. Things start off, pink, yellow, and they end up getting burnt. They go through a brown phase, and then they get up. Everything does, right? All right. When does the cooking chicken create the most grease? What number? 2.5, 3. That's what I think. So I made a little plot here, and it say, the greasy stuff is somewhere around in here, right? Up here, it's undercooked, it's yuck, right? Down here, it's overcooked, it's burnt. But somewhere in between, it gets greasy. All right? All right, how can we use our chicken scale? All right? See this? Black, dark brown, brown. Exact same numbers, right? See, right? This thing here is from a proprietary study of how to tell if there's oil present in a rock. All right, so this is it. So what they do is they use this plot. They don't use it, they're not talking about chickens. And they look at the spore coloration index, called the TAI, the thermal alteration index. And here are the colors of it, yellow, orange, dark orange. And they look at little tiny pieces of organic material, and they assign colors to it. And if they don't use that, they might use something called the Rockavel. This is a special oven they use to cook organic matter in samples. And they have different temperatures, and they tie that to the color formation as well. If they can also look at the shininess of little organic matter, and that's called the vitrinite reflectance. Vitrinite's a type of wood maceral or wood fragment. And then approximate temperatures, so on and so forth. So this diagram here, shown in black and white, predicts where oil will occur in a basin. So they say that if you look at the vitrinite reflections, the shininess of little organic matter, or if you look at the color of spore color from little plants, and you're in the dark orange area, that's when you form the main phase of gas generation. Here's where they form the main phase of oil generation. So you have to go to that depth. This is the prediction of how deep you have to drill in a basin to find oil and gas, and it's the exact same temperature scale that you'd use for checking a cooked chicken, which is kind of interesting. I guess I took this from a geologic journal. Okay, so what happens when you mix grease and water? So here is our chicken, and here we have water on top. What happens when you mix grease and water? Grease rises up like that. So here's our cooked chicken. So we're cooking the chicken in the geologic basin. The oil's coming out, it's in water, and it's floating up to the top. So what happens is, here's our source rock, which is the Miocene anoxic mudstones formed by coastal upwelling. They're heated to that right temperature, which is the same as making your chicken to the right temperature. And then the oil's released, and it floats up until it's trapped. All right? So when we cook our chicken, the grease in the rock separates, making an oil accumulation if there's a trap. So you have to trap it somehow. The source rock is the chicken heated to the temperature of grease formation. Grease rises from the source rock into the porous and permeable reservoir rock and separates from the water. The oil and gas is trapped under the impermeable cap rock in the anticline. So that's how we make oil in the LA Basin. So thought question, if you take an organic rich shale like the Monterey Formation and bury it to a depth of, exposing it to temperatures of 200 degrees Fahrenheit for millions of years, what do you think happens? Well, you'd form the oil here, and it's going to go get trapped in the structure, right? And that structure is formed again when the LA Basin closes and we folded all those rocks up, right? So here's what different oil fields look like. I just grabbed these from the literature. So we have some sort of deformation going on. Remember, we're going to fold up those Monterey Formation rocks. We're folding things up. And as you're doing that, you're heating up that source rock. It goes up, and those sandstones, those deep water sandstones, get filled with oil. And that's sort of a very cartoon-like history of the LA Basin. So, oil field maps. Here's California. Almost all of the oil in California, probably 70% of it is from the Monterey Formation. So I worked in Bakersfield for 15 years, and basically all of these oil fields down here are from the Monterey Formation. There's another unit up here that caused those oil fields. We're down here in the LA Basin. Essentially all of that oil is from the Monterey Formation. All right, here is a blow-up showing what California looked like in 1930 in terms of oil field development. Those are all the oil fields that we're dealing with, and they're gigantic oil fields. This is from the Department of Conservation, what we call the Dogger Division of Oil, Gas, and Geothermal Resources of State of California. And this is showing all the wells that have been drilled. Here's Palos Verdes, here's Torrance, we're down here, here's Newport Beach, here's the Back Bay here. And these are all the oil fields and all the wells that have been drilled. And some of these are, looking for new oil fields. And they didn't find any, so that's why the well's all by itself. But if there's giant clusters of wells here, that means that they're developing some sort of oil field. So these are all the different oil fields here. And then again, here's places where they drilled. They got geologic information, but it wasn't enough to make it into an oil field. This one of the most famous ones is Signal Hill. You all know Signal Hill, right? As you drive by Cherry Avenue in Long Beach and so forth, that innocent-looking little hill, which will also figure prominently in the Newport-Inglewood Fault next time. Well, here, the Cherry Hill Fault is essentially one of the Newport-Inglewood faults. At any rate, that thing, it was figures prominently in that book Oil by Sinclair Lewis that was made into the Daniel Defoe movie, Then There Will Be Blood or whatever. So all of that, that was the name of it? Then There Will Be Blood?
Close.
Something like that. What was the name of it? There Will Be Blood, right, thank you. All that was about L.A. and surrounding areas back in the 1930s, 1920s. It was a Wild West town. So the roots of LA, Orange County, was very much in the oil industry. And this is showing what Signal Hill looked like, I don't know what, 1923. And another view of Signal Hill. So oil derricks just everywhere. And of course, for us, this is Huntington Beach. So this would be... here's on the pier, and that's showing a lot of oil derricks. This is what we call the Huntington Cliffs, just north of the pier. Bazillions of oil derricks. So how much oil is left? A buddy of mine did this study out of the U.S. Geological Survey, assessment of 10 oil fields. One of the things about producing oil fields is when you did it back in 1930, you didn't have a clue. And when you do it today, you have a clue. So we're much more successful at getting oil out of the ground now than we were 100 years ago. But a lot of the oil fields were done back in 1930. So a lot of the oil is still left in the ground. Now the problem is when you build a city on top of an oil field, you basically don't go back to the oil field because there's a city on it, and people don't like oil derricks and pumps in their backyard. But at any rate, just for the sake of assessing what is in our United States, the U.S. Geological Survey went back and they studied all the oil fields in the contemporaneous United States, conterminous. At any rate, and this is for our area here. So, for example, in the Seal Beach oil field, it's OOIP means original oil in place. BB means billions of barrels. Okay, so to me, a big oil field, I think it's defined as more than 500 million barrels. So here you have 850 million barrels. Okay, but today, EUR's estimated ultimate recovery, billions of barrels, is about 220 million barrels. That's the recovery factor. And the remaining, so they think they might be able to get another 100 or 200 million barrels of oil out of Seal Beach if there weren't houses all over it. So Wilmington is a giant field. The Torrance field is giant, up to 2 billion barrels of oil, maybe anywhere from 100 million to 400 million barrels of oil. Okay, so back in the day, 10 years ago, oil was selling for $100 a barrel. 100 million barrels times 100 would be worth 100, be $10 billion, right? So this is a huge amount of money associated with this that will never be touched because you've got houses all over it. And also, back in the day, we didn't really understand climate change. And, you know, a lot of we're going to probably leave a lot of oil in the ground because of the CO2 problem. So the whole glory of the oil industry has really lost its charm because of the global climate change. Yes?
Those figures would seem to be much more valuable land value than what you would have for housing value. I mean, you don't find hundreds of millions of dollars for land value for some of these projects, right, or billions of dollars.
No, okay, so the problem is, the question is say Seal Beach is worth, here's 100 million to maybe 200 million barrels of oil that may be recoverable. Okay, the problem is there's probably 1,000 houses on that. Each house is worth $1 million. So 1 million times 1,000, so that's like $1 billion there or something like that. So the problem is, okay, So first of all, you'd have to buy all the houses in a great area, swath of area. Secondly, that cuts down your profit margin right there because you've had to spend extra money. If, amazingly enough, if there's just oil under the ground and there's no housing problems or anything around, getting the oil out is really expensive still. I mean, all the easy oil's been taken out. So to get the dribs and drabs out, you have to use fancier techniques. For example, in Bakersfield, we did phenomenally well. We drained up. These typically drain up to about, 20, 30. If you get 30% of the oil out, you're doing great. In Bakersfield, we're getting 50 to 60% of the oil out, but we're using steam. What they're doing is they pump steam in the ground. That makes the oil flow like water.
Is that fracking?
No, that's not fracking.
Okay.
Wait a sec. Let's not get confused. Anyway, so steaming, basically like cleaning out your shirts. It cleans out everything. It just removes all the oil, but you have to pay for the steam. And steam's, it's very expensive to make, tons and tons of gallons and barrels of steam. So every time you go in to get these things, it's not cheap. So I'm sure that no oil company in the world would look at this and go, ooh, an opportunity, because there's houses everywhere. And California also doesn't like you doing that sort of thing anyway. Yes?
Does this include the offshore Long Beach oil that they're going out under here?
Here's the Long Beach field, and I'd have to go back to the paper to check. Probably it does, though. I'm pretty sure it does.
Do they slant drill?
Okay, well, this is just how much. Okay, the question is, do they slant drill? This is just saying what type of resource is there. Okay, how much oil could we, if we were really desperate, how much oil could we get? How you get it out, whether you're fracking it, slant drilling it, or whatever, is just a technicality that typically adds to your price. So if all your wells are slant wells, they're going to be a lot more expensive than a vertical well. So that's going to add 30% on to your prices. So before we drilled any well at Chevron, we calculated the economics for everything. Okay? A lot of times, oil companies don't do that, and that's why they get into hot water. That's why Chevron's doing really well, is because they go nuts on the economics. They want everything down to the last penny. Occidental used to just drill wells sort of almost for the hell of it, just to see what they'd find. What we call a cowboy approach, where you just go, yeah, let's go get them, and like, oh, we just spent $5 million and didn't find anything. That's not a good thing. Chevron, they'd be, angst about it. Yes?
I know in Hermosa Beach, they're like taking a site that's no bigger than a house, and they're doing slant or horizontal drilling, and the people there, they want to do it, and the people there are fighting it. But since it's only one little site and they have rights, it's a real problem.
So there's passions run high associated with it, and that's a whole nother world that we're not talking about. All I'm really bringing up here is that today, when we drive around LA, we've kind of lost a little bit of the history, which was an oil boom town. So LA was an oil boom town 100 years ago, in 1920s, right? And that's why Sinclair Lewis, by the way, if you've ever read the book Sinclair Lewis called Oil, that movie was based on, it's just a gripping tale. And by the way, we could go on to fracking and everything else. Let's see, we have a few minutes left, and I think I'm getting to the end. Final thought: Los Angeles Basin, most prolific and most urban petroleum province in the world. The Los Angeles Basin is the most productive basin by area. We mentioned this before. And the Monterey Formation is the source of this. So summary: the rotation of the Santa Barbara Block unroofed the Catalina schist. We all talked about this, which had been buried deeper than 20 miles. The rotation of the Santa Barbara Block led to the formation of the Los Angeles Basin by extending the Earth's crust, pulled it apart, made a hole. The Los Angeles Basin filled in part with the Monterey Formation. When the Monterey Formation was buried to the right temperature, about the same as cooking a chicken, it formed oil. When the Los Angeles basin was squeezed by tectonic processes, huge quantities of oil migrated into structural traps, and we live in a magical place. The rotation of the Santa Barbara block unroofed the, oh, I already did that. Oh, and this just shows the oil wells at Huntington Beach, and look at the bazillion wells that we see in the area. By the way, what happened when Santa Barbara block slammed into Santa Maria? This is another one of those cross sections showing the collision of the Santa Barbara block with the Santa Maria area. And with that, I think we're back to the beginning. So that ends our second lecture. Next time, we'll talk about how the Tanya Atwater model addresses the earthquake issues. So we'll talk about the rotation of the Santa Barbara block and all the different types of earthquakes we have around, how to and probability of the next earthquake, paleoseismic, old earthquakes, who's famous in the area of earthquakes around here, everything you wanted to know about earthquakes and more. And then the last talk will be on the ice ages in our neighborhood. Excuse me? Any questions? They're gone.
You just anticipate.